Hello, YouTube. I think it's no surprise to anyone if I say that I'm a bit of a nerd. So it should also be no surprise to you if I let you know that back when I was in college, one of the first big book purchases I did was to purchase the 13 books of the elements. What's that, you might be wondering? It's the famous book on geometry by Euclid. What may be more astonishing is that I've actually read a large chunk of those books too. Not all of them. I may be a nerd, but I'm not insane. In any case, what makes Euclid so beneficial is that he was pretty much the first mathematician to try to organize geometry into systematic proofs. It's not to say it wasn't done by others, of course. Most likely Euclid wasn't inventing much new material at all, but he was instead collating all the knowledge and putting it together into a single source. But the important part of the work was that Euclid began by providing certain postulates that one had to assume to be true. They could not be proven, but instead they were the basis by which all else could be proven. So you start with the postulates and the axioms, and then what Euclid did was to use those to prove propositions. A proposition, once proven by the postulates, could then be used to prove other propositions as well. From this, all that we know about Euclidean geometry came about. Now, what are the axioms that Euclid used? They're actually pretty straightforward. The first axiom is things which are equal to the same thing are also equal to one another. Second is if equals be added to equals, the wholes are equal. Third is if equals be subtracted from equals, the remainders are equal. And the fourth one is things which coincide with one another are equal to one another. The fifth axiom is the whole is greater than the part. Now, some of the wording there is a bit esoteric because the Greeks didn't think of mathematics the way we do today. Today we use algebra to help symbolize certain things. For instance, the first axiom, things which are equal to the same thing are also equal to one another, can be expressed by saying if A equals B and if B equals C, then A equals C. But again, the axioms are fairly obvious and make sense. We can see why we can assume them to be correct without proving them to be correct, since we can't even begin to reason about geometry without those axioms in place. But what about the postulates? So just as there was those 5 axioms, Euclid had 5 postulates too. Those are 1, to draw a straight line from any point to any point. 2, to produce a finite straight line continuously in a straight line. 3, to describe a circle with any center and distance. 4, that all right angles are equal to one another. 5, that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the straight lines, if produced indefinitely, will meet on that side on which the angles are less than the 2 right angles. Now again, the language here is a bit esoteric, but even setting aside the odd language, which has been updated by Wolfram to make it easier to understand in today's English, it should be immediately obvious that one of these postulates isn't like the others. While the first 4 postulates are short and to the point, that 5th postulate sticks out like a sore thumb in its complexity. The first postulate is simple. You can draw a straight line between any 2 points. That's simple and clear. The second, equally so. You can extend any line segment indefinitely in a straight line. The third tells us that given a line segment, you can always draw a circle having that line segment as the radius with one endpoint being the center of the circle. And the fourth one tells us that all right angles are congruent. They're equal to each other. But what is the 5th postulate telling us? In simpler language, this is equivalent to the so-called parallel postulate, namely that if 2 lines are parallel, they will never intersect. Euclid states this in the inverse manner, which is to say that if you intersect 2 straight lines with another straight line in such a way that there are not 2 right angles formed at the intersection of that third line, then the lines will meet on the side where the angles are less than the 2 right angles. That's a mouthful to say though. Given the fact that postulates are unproven assumptions, the simpler the better. The more complex an unproven assumption is, the less reason we have to accept it as being valid. And in fact, the 5th postulate is complex enough that for centuries mathematicians were certain there had to be some kind of way to prove it. Euclid's genius was in realizing there was no proof for it. It was a postulate. But of course, by the 1800s, mathematicians were asking, what if this unwieldy postulate is unwieldy precisely because it's not true? It's certainly possible to do as Euclid did and assume that parallel lines never meet, but since this is an unproven assertion, then there's nothing in mathematics keeping people from assuming that's actually false. Not only that, but assuming the fifth postulate is false might be able to give us an inconsistency somewhere else in geometry, which would then give us the ability to prove the fifth postulate by the impossibility of the contrary. Now, there are two different ways in which one could say the fifth postulate is false. Instead of saying that parallel lines will never meet, one could argue that parallel lines repel one another, that is, they curve away from each other. Or one could say that parallel lines attract each other and always converge. So that's easy enough to adjust. We can say the fifth postulate is false in each of those ways, look for contradictions, and refute non-Euclidean geometry. Except, of course, it turns out that both of these alternate understandings of the fifth postulate result in consistent geometry. There is no fundamental contradiction. To be sure, the different views contradict each other, but each view is self-consistent. The truth that parallel lines repel one another, you end up with hyperbolic geometry. Assuming that parallel lines converge, you end up with elliptic geometry. If truth is measured by the fact that a system is consistent with its own axioms, each of these views is equally true. But the question remains, which one is true of the physical universe? After all, mathematics can be true in theory and can be useful in a purely noetic sense, but the science of physics, for example, requires mathematics to have a real-world application, not just a theoretical application. Does the universe tell us whether physical space is Euclidean, hyperbolic, or elliptic? There is one way to possibly tell. If space is Euclidean, then a triangle will always have angles that add up to exactly 180 degrees. If the universe is hyperbolic, then adding up the angles will give us a result of less than 180 degrees. And finally, if physical space is elliptic, then a triangle will have angles greater than 180 degrees. So all we need to do is pick 3 points in space, measure the angles between them, and see what those angles add up to. Sounds simple. But there's a slight problem with that. The universe is really, really big. I'm not sure if you've noticed, but it's huge, like the size of my ego. Given how massive the universe is, in order to measure our physical points with any kind of validity, these points would have to be very, very far away from each other. That's because clearly at short distances, the universe must be very close to Euclidean. If it wasn't, we would have noticed. But just because short distances appear to be Euclidean doesn't mean that 3.5 billion light years from each other won't demonstrate a slight curve. If the angles of a triangle add up to 180.0000001 degrees over that 5 billion light years, then the universe is not Euclidean. And given the enormous size of the known universe, such a small departure from Euclidean geometry can end up having massive geometrical consequences. The upshot is, given our current technology, it's impossible to measure angles precise enough for us to know whether or not physical space is Euclidean, hyperbolic, or elliptic. We do know that locally it's close enough to Euclidean that for all our experiments on Earth, we can assume Euclidean geometry. But such an assumption just cannot be held over the entirety of the universe, and the actual shape of the universe could have big implications on whether the universe is heading towards a heat death or a big crunch. And which of those is going to happen may have pretty large ramifications for the philosophy of science even today. So there you go. We have 3 self-consistent systems of geometry based on whether one accepts an unproven postulate in geometry, or, if you don't accept that, the manner in which you reject it. None of these can be empirically proven. Any one of them might reflect the reality of physical space. All of this showing that the more you know you don't know too. I hope you have fun thinking about all that, and as always, have a wonderful day. Peace out.